All right, so all right. Okay, do you see my screen now?
Yep, we can see it. Yep.
Do you see the presentation?
Yes.
All right, I'll try to turn it off. Yeah, all good
Yep.
now?
Yep.
All right, again, thanks a lot for having me. Perhaps my talk will be not kind of like completely in line to everything that you have heard before, because as you can see from the title, it's about using computational models in response to COVID-19 pandemic. My name is Mikhail, and indeed I have double affiliation, so I'm working here at the lab, and I also worked on the project, a European project that's called HEROES for TU Delft. Right, so just a recap. So where we are now, it's almost a year since the pandemic has started. It was registered, and well, ideally, right, so given the crisis, this is not the first pandemic that we have faced. So ideally, we would like to learn and already kind of like, we would like to see this curve going down, right? But apparently it's not going down. It's like a chainsaw here, and we are kind of not doing really great. And also, well, the thing has started kind of like a pretty some time ago. And we made some actions. Here you see the graph, for example, for Netherlands, how the country was dealing with the pandemic. So, and the experts kind of knew that the second wave is coming, but somehow like we didn't really manage to do anything about that. So as you can see, somewhere around October, actually September, where people get back from holidays from different places, when they start to interact pretty much more than before, the curve started to go up. So, and we started questioning ourselves, like, what are the bases and how do we make decisions and what we can do to actually tackle this problem, right? Because we already have been in this place for some time, but it's not getting better. So, and well, let's try to sketch some approaches that are there for the policy making, so to say. So, of course, this is oversimplification, but so we have a top-down approach when the national government decides what to close. For example, like let's close the schools, let's close universities. This is responsibility of national government in the Netherlands. You have bottom-up approach. For example, in Canada, you have provincial government. Well, they are responsible for healthcare, and they are thinking about, all right, so like in this specific the province that we have that we are now, so we'll do like closures, some sort of closures. And we have mixed approach in Russia. So when you have a national government who is saying something like, all right, so you need to perhaps follow social distancing and do certain things, but you also have a central government that is saying that you need to do something a bit different. Well, and of course, the reality is a bit more complicated than that. So we have multiple actors involved in the decision making. And it's really kind of like a complex process when you don't really know who's responsible, who is doing what. And yeah, probably this is one of the reasons why infections are still go up. So, and how do we make the policies? Well, this is more about approach and what is the base for the policy making. So we have some countries who have some experience in dealing with the pandemic before, for example, China and South Korea. So they have also a very, how to say, very nice and useful culture of wearing the masks. So this is one of the pillars of their actions. You also have expert opinions. You have WHO who providing the recommendations, what you need to do. You have organized within different countries national emergency groups, and you have healthcare experts who are saying what needs to be done. And the final part is using the computational models. So in the Netherlands, you have the national agency called RIVM. They built some models, computational models that they're using to understand how the pandemic evolves. You have Imperial College with also very famous, perhaps notorious model for their bugs there and so on. And you, for example, you have a CommonKit model for Vietnam. So, and what is computational model actually? Computational model is a mathematical model in computational science that requires extensive computational resources to study the behavior of a complex system by computer simulation. So basically it's a program, right? So you kind of like, you first sketch some math and then you try to transfer this math into a program, some software that you'll push the button and you will see something like this. So I think for now, we all familiar with the curves. Here you see the curves on the left. These are infection curves. And of course, we all know that the pandemic is the thing that is kind of like very unequally distributed over the space. And you see that some infections are developing elsewhere here. So, and how the oversimplified interaction between the policymakers and researchers who are building the models can look like. You have two actors here, right? So this is oversimplified graph. Policymaker and researcher. Policymaker formulates the problem and a certain list of policies that they would like to test. For example, close schools, close universities, close bars, close some, I don't know, museums. And researcher starts to build a model. All right, so we have certain set of tools, and let's try to really come up with something that is very prepared for this specific problem and for these policies. Then researcher run the model and then provide the policymaker with a set of plausible scenarios. Okay, so given the policies that you want to implement, these are the potential how the disease will evolve. And the next part that is pretty complicated, right? So since the policymaker is provided with a set of plausible scenarios, but he needs to make a policy decision, right? And ideally, it shouldn't be completely based on the expert opinion, right? He is taking into account like his political party's interest, like economy and all of these factors, and then he's making a political decision. And ideally, there should be a feedback loop when we implemented the policy, and then we see how the thing is changing, how the pandemic is evolving. There should be a feedback loop when we can again go back and try to improve the model with new inputs. Yeah, so here, now I would like to give you some concrete example, how we build that, how we did that. So again, my work here that I'm presenting here is a part of European project. We have 9 universities that collaborate with us, universities from Poland, from Finland, from Italy, Red Cross, and multiple parties. So you can read more about the project here. So all of the reports that we already kind of prepared also stored there. And behind this work, we have a group of people who actually work hard on that. So that's myself here, somewhere in the middle, and some research assistants, professors from TU Delft. Right, so I won't really go very technical with what we have built, just to give you a sort of like sense how the model looks like and what's that actually. Meet Emma. Emma is kind of like a prototypical agent in our model. So, and here what we know about her. Emma is 42, she's single, she lives in a very specific neighborhood in The Hague. This is the model that is built for the city of The Hague. He works in an auto repair shop and he has an average income, and she owns a car and she uses to get to work. So here is just a prototypical agent in our model. Let's take a look how the day in the life of Emma could look like. Here is a map of The Hague, and you have a couple of points highlighted here. We'll try to zoom into the place where Emma lives, and she starts her day from some typical activity. She takes a breakfast and starts to do some personal care, prepare to go to work. She goes to work by car, and finally she arrives to work, and she works there for around 9 hours with her colleagues. Then she all of a sudden decides to have a nice dinner in a restaurant nearby. She invited her colleagues there and her friends. So they having a dinner. And by the end of the day, she also decided to go to a supermarket nearby. And then, as all she's supposed to end up somewhere to get home somehow. This is the core of our model, and what is important to understand. So since we're talking about the pandemic, right? So how did Emma get infected? So she worked with Josh for 8 hours, and Josh in his turn got infected from his son, who is a student. They both, Josh and his son, are asymptomatic. That makes it a bit more complicated to understand what actually happens for him. Well, and again, so in a nutshell, what we built is about different people in our model. They do different activities at certain locations where they meet each other and they can get infected. So this is the model intuition behind the thing that we have built. And so just again, to give you a sort of like a sense of how the model could be useful for policymakers and what is the outcome, so to say. So we can try to analyze and try to see the number of infected people in the city. So, well, we all scientists, we really like to plot graphs here. And here is, we have some sort of good graph. When you have on the x-axis, you have a time. So from March till June. And on the y-axis, you have a number of infected people in the city. So, and you can see that we have 3 colors here. So you have orange color, blue color, and green color. Here, those colors represent different policies that policymaker kind of ask us to take a look at and to test. And the orange one is what will happen to the number of infected people if you won't do anything, just like, okay, no closures, no limits on anything, just continue run the city as usual. Then we try to also study soft lockdown. As you can see here, we try to close educational institutions, bars, and entertainment facilities. So that's supposed to be interesting for us. So to understand whether or not the closure of educational institutions actually adds any difference. Finally, we have a hard lockdown here when you close everything besides emergency services, supermarkets, and pharmacies. Well, as you can see from these graphs, the graphs are actually a combination of scenarios, but don't really think about it that much. So just let's focus on the lines themselves. So we have a blue line, we have a green line, and we have orange line, right? So as you remember, we have blue is a closure of educational institutions, and orange is do nothing. So there is no such a big difference here. So well, if we will close only educational institutions, bars, and entertainment, so it's almost similar to do nothing policy. So basically, there is no point in doing that. On the contrary, so if you do a hard lockdown and if you will left only emergency services, supermarkets, pharmacy open, the disease goes down. So basically, the conclusion from that is that soft measures may not work, and the number of social interactions happening in the places that are open, specifically supermarkets and pharmacies, are still too high, and it can kind of like make the pandemic continue to run as it was before. Yeah, and something pretty interesting from our model about the supermarkets. So again, the graph, x-axis time, y-axis number of people infected, and these are the infections that happen at supermarket. So if you do a hard lockdown and if you close everything, as I said before, yes, but if you leave only the supermarkets open, so the number of infections in supermarkets is kind of like very, very high, because basically this is the only one place where people meet. And yeah, so you also see the spikes here, and this is the typical visiting time of people around 5 o'clock. Yes, and it's really different from do nothing policy, because if you don't close anything, so people will get infected elsewhere, not only at supermarkets, right? So basically, so the conclusion from that graph, from that, so that we need to really prevent the crowding and manage the number of people that are visiting supermarkets. Well, to conclude, here's a famous quote from George Box that we build a model, but we kind of like always keep in mind that all models are wrong, but some of them are useful. So this is just a tool to understand the reality, so to say. This is a useful instrument for sure, because it's better to have a certain sense how different actions, different policies can affect the reality. But again, so I wanted to stress the fact that, well, the models are provide you with a sort of like insight, what could be, but the decisions are given to politicians, and it's always a political decision, right? So politicians are driven by interests of many, many parties. It's much harder just to give some numbers and just argue, okay, this is what could happen. Yes, and finally, so I want to also stress the fact that in our case, we do not predict. So you perhaps often hear from elsewhere that, all right, so our predictions shows us that the infections will go down somewhere in March. So like in this project, we strongly kind of like advise against that. So we're not predicting, we're just like exploring what could happen. So, and the difference is that like, there is absolutely no way to predict when the phenomena that you try to study is so complex. If we could predict, we're just doing that, and we won't have such a extreme curve like going up every day with the breaking records. Yeah, thanks a lot again for having me. That's it.